This is Richard Hammack's Calculus 1. We are in part 4 of the course on applications of derivatives. This is lecture 37C. It's our third and final installment on indeterminate forms and L'Hopital's rule. You'll remember that in lecture 37A we introduced L'Hopital's rule, which is a means of dealing with limits of indeterminate forms 0 over 0 or infinity over infinity. In lecture 37b, we learned how to apply L'Hopital's rule to two new indeterminate forms, limits of form 0 times infinity, or infinity minus infinity. Today in lecture 37c, we will introduce three new indeterminate forms, 1 to the power of infinity, infinity to the power of 0, and 0 to the power of 0. And we'll see how to use L'Hopital's rule to evaluate limits that have these forms. A quick reminder of L'Hopital's rule. It states that if the limit as x approaches c of f of x over g of x has indeterminate form 0 over 0 or infinity over infinity, then the limit as x approaches c of f of x over g of x is equal to the limit as x approaches c of f prime of x over g prime of x. And we also learned how to apply L'Hopital's rule to the indeterminate forms 0 times infinity and infinity minus infinity. As a quick warm-up example, I want to do a limit of form 0 times infinity because that technique is going to be key in what we do today. Think of the limit as x goes to 0 of x times cotangent x. The x is approaching 0. And what about cotangent x? If you think about the graph of cotangent x, there's a vertical asymptote at x equals 0. So as x approaches 0, cotangent of x is going to infinity, or minus infinity, depending on how x is approaching 0. But basically, you're getting some form of infinity in the second factor. So this limit has form 0 times infinity. We learned last time to handle a limit like this by keeping one factor at the top and bringing the other factor down to the bottom as its reciprocal. And let's leave x at the top because x has a really simple derivative. And we'll bring cotangent x down to the bottom as 1 over cotangent x. Now, 1 over cotangent x is tangent x. So we have the limit now as x goes to 0 of x over tangent x. So as x approaches 0, the numerator goes to 0, and also the denominator tangent of x approaches 0 as well. So this limit has form 0 over 0. So we've converted infinity times 0 up here to 0 over 0 here. And we can use L'Hopital's rule at this point. L'Hopital's rule says that this limit equals the limit as x goes to 0 of derivative of x on top and the derivative of tangent x on the bottom. This limit is incredibly simple. Secant x is 1 over cosine x. So x goes to 0, that's turning into 1, and its square is turning into 1. So we just get 1 over secant squared 0, which is 1. And there we go. This limit equals 1. Let's move on now to our main task for today. We have three more indeterminate forms that I'll introduce on this slide. And I'll do this by example. Consider the limit x approaches 0 of the quantity 2 to the power of x raised to the power of 1 over x. The exponents would multiply, so you're raising 2 to the power of x times 1 over x, which is just 2 to the power of 1. So this limit is transparent. It works out to 2. But look at the structure that it has. X is approaching 0, so this base 2 to the power of x is approaching 2 to the power of 0, which is 1. So you're getting 1 as a base. And the exponent, 1 over x, is going to infinity as x approaches 0. This limit has the form 1 to the power of infinity. And we got an answer of 2. Now consider the limit as x goes to 0 of 3 to the x to the power of 1 over x. It's just the same limit we did before, but I've changed the base from 2 to 3. Once again, the exponents multiply, so you can see that this limit equals 3. The 3 to the x is approaching 3 to the 0, which is 1. The 1 over x is approaching infinity as x goes to 0. So this limit has the form of 1 to the power of infinity, as did the previous one. We would say these two limits have the form 1 to the power of infinity. And you can see here that 1 to the power of infinity is an indeterminate form. By itself, 1 to the power of infinity doesn't make any sense, but you can have limits of that form that give you different answers and that do make sense. Let's move on. Here's another limit. It's really just the same as the one we had up here, but instead of x going to 0, x is approaching infinity. As before, 2 to the x to the power of 1 over x equals 2, so this limit clearly evaluates to 2. But look at the form that it has. 2 to the power of x is the base, and x is going to infinity, so 2 to the power of x is going to infinity. But what about the exponent 1 over x? X is going to infinity, so that's turning into 0. So we have here a base approaching infinity raised to a power that's approaching 0. This limit has the form infinity to the power of 0. Just change that base to a 3, and you get a related limit that equals 3. It has the form of infinity to the power of 0 also. These two limits are of form infinity to the power of 0. So you can see here that infinity to the power of 0 is indeterminate. It doesn't make any sense by itself, but you can have limits that have that form that do make sense and equal different numbers. Here's another example. Think about the limit as x goes to 0 of x to the power of 0. Now as x goes to 0, it's not 0, just getting closer and closer to 0. Any non-zero number to the power of 0 is 1, so x to the power of 0 is just 1 for all of those x's. So this limit equals 1. But look at the form it has. X approaches 0, so we're getting 0 to the power of 0. This limit has form 0 to the power of 0. And here's another one. The limit as x approaches infinity of 2 to the minus x to the power of 1 over x. What's happening here? X is getting bigger and bigger and bigger, so 2 to the negative of that x is 1 over 2 to the x. That's shrinking to 0. And likewise, as x goes to infinity, the 1 over x approaches 0. So this limit also has form 0 to the power of 0. But it's easy to work out this limit. Just multiply these two exponents, and you get 2 to the power of minus 1, or 1/2. So each of these two limits had the form 0 to the power of 0. In one case, you got the answer of 1, and the other case, you got the answer of 1/2. These are two limits of form 0 to the power of 0. So you can see that's an indeterminate form because you have two different limits that have that form, but they work out to different numbers. By itself, 0 to the power of 0 doesn't make any sense at all, but you can see here that you can have limits that have that form that do make sense, and they can be equal to various numbers. So we have here our three new indeterminate forms. And altogether, we have 7 of these indeterminate forms. We have 0 over 0 and infinity over infinity that L'Hopital's rule applies to. In lecture 37b, we talked about 0 times infinity and infinity minus infinity. And now today, in lecture 37c, we have these 3 more indeterminate forms. So altogether, there are 7 indeterminate forms, and there aren't any more. I should mention that there are lots of forms that are not indeterminate. a limit of form 0 over infinity. You've got a value that's approaching 0 divided by a bigger and bigger number. That equals 0. That's not an indeterminate form. You can say what that is. Likewise, infinity divided by 0. The top is getting bigger and bigger, divided by a smaller and smaller number. That quotient is getting bigger and bigger. So infinity over 0 is infinity. It's not indeterminate. 0 to the power of infinity. Think about a really small number like maybe 1/2 or 1/4 raised to a really big power. That's very small. And the smaller the base gets and the bigger the exponent gets, the closer and closer that value gets to 0. So 0 to the power of infinity is not indeterminate. It's 0. Infinity to the power of 1 is infinity. That's not indeterminate. Likewise, infinity to the power of infinity, you can reason out, is infinity. And 1 to the power of 0 is 1. That's not indeterminate. So watch out for forms that may pop up in limits that are not indeterminate. You don't need L'Hopital's rules for these. But we do have these 7 indeterminate forms that L'Hopital's rule can apply to. So our task for today is to figure out how to use L'Hopital's rule for these last 3 remaining indeterminate forms. And I'll show you how to do that. Just one technique will work for all 3 of these. And that technique is going to involve the ln function. So let me first remind you of a few facts about ln. Its graph looks like this. Its x-intercept is 1, that is, ln of 1 equals 0. And also, the limit as x approaches 0 from the right of ln is negative infinity. The graph just goes straight down. And remember, ln is not defined for negative numbers. Also, remember this property. This will be important. Ln of b to the a equals a times ln of b. And finally, any quantity whatsoever, or any positive quantity, equals e to the power of ln of that quantity. That's because ln of x is the inverse of e to the x. So e to the ln of a quantity equals that quantity. All of these properties will be needed in our technique. The technique is really kind of a trick, but it works beautifully. Here it is. Suppose the limit as x approaches c of f of x to the power of g of x has one of these 3 indeterminate forms. Like for the first one, f of x is approaching 1 and g of x is approaching infinity, and so on. Here's what we are going to do. The limit as x approaches c of f of x to the power of g of x, this limit, equals the following. We're going to replace this quantity f of x to the power of g of x with e to the power of ln of that f of x to the power of g of x. Remember, f of x to the power of g of x equals e to the power of ln of f of x to the power of g of x by this property. So we go from here to here, and look at what we have. E to the power of ln of a quantity to a power. Remember that whenever you have ln of something to a power, like ln of b to the a, that exponent can come out in front of the logarithm, a times ln b. In this case, that g of x way up there can come out in front of the ln, and this limit is now limit as x goes to c of e raised to the power of g of x times ln of f of x. And you will find in this case that no matter which of these 3 indeterminate forms you have, if you cover up that e and just look at g of x times the function ln of f of x, that g of x times ln of f of x, it's going to have form 0 times infinity or infinity times 0. And we can handle that. We know how to use L'Hopital's rule to handle this indeterminate form. So that's our trick. And I'm now going to work out 3 examples showing this trick. One example for each of these indeterminate forms. Example 1. Limit as x goes to infinity of the x root of x. Maybe that looks a little strange, so let's convert it to a power. The x root of x is x to the power of 1 over x. So we get this limit. X is going to infinity, and that base x is going to infinity, and the exponent 1 over x is approaching 0. So this limit has form infinity to the power of 0. We're now going to use our trick outlined on the previous slide. Remember, when you have an indeterminate form f of x to the power of g of x, what you're going to do is take e to the power of ln of that. Our limit becomes limit as x goes to infinity of e raised to the power of ln of x to the 1 over x. And remember, e to the ln of this just equals what you had up there. So you haven't changed anything. Our next step is to bring this 1 over x down in front of the ln using an ln property. So we get the limit as x goes to infinity of e raised to the power of 1 over x times ln of x. And here, to make this simpler, let me bring this limit up into the exponent. Remember, e is a continuous function, so we can do that. We get e raised to the power of the limit as x goes to infinity of 1 over x times ln x. Forget about the e for just a second and look at the limit that we have. X is going to infinity, so 1 over x is going to 0, and ln of x is approaching infinity. So this limit, this exponent up here that you're raising e to the power of, is of form 0 times infinity. And that's one of the indeterminate forms that we can handle. In this case, it's pretty simple. Normally you'd bring one of these terms down to the bottom as its reciprocal, but it's just quicker just to multiply this 1 over x into the ln of x, and we get e to the power of e to the power of limit as x goes to infinity of ln x over x. Looking at this limit, x is going to infinity, so ln of x is also going to infinity. So this limit that e is being raised to has form infinity over infinity. So we can use L'Hopital's rule on that limit. And let's do so. Just bring down the e and apply L'Hopital's rule to this limit. We get the limit as x goes to infinity of derivative of ln x, which is 1 over x, divided by the derivative of x, which is 1. As x goes to infinity, 1 over x approaches 0, so we get e to the power of 0 over 1, which is e to the power of 0, and e to the power of 0 equals 1. So this limit of form infinity to the power of 0, by our new trick, worked out to be 1. Example 2. Let's do the limit as x approaches infinity of 1 over x plus 1 to the power of x. And we'll analyze what's happening here. As x goes to infinity, this base is, let's see, the 1 over x is going to infinity, so the 1 over x is approaching 0 plus 1. This base is approaching 1, and it's being raised to the x, which is approaching infinity. This limit has form 1 to the power of infinity. And remember, that was another one of our 3 new indeterminate forms. So let's apply our trick to this limit. Our trick is to replace the 1 over x plus 1 to the power of x with e to the power of ln of that 1 over x plus 1 to the power of x. And again, remember, e to the power of ln of all of this just equals what we had above. So we haven't changed anything, except that we're putting it into a more convenient form. Our next step is to use an ln property to bring this exponent of x down in front of the ln. So we get limit as x goes to infinity of e to the x ln of 1 over x plus 1. Next, Using the fact that e to the x is continuous, we can bring this limit up into the exponent, and we get e raised to the power of limit as x goes to infinity of x ln 1 over x plus 1. Look at that limit in that exponent. X is going to infinity, and it's multiplied by ln of 1 over x plus 1, and as x goes to infinity, the 1 over x approaches 0, and that plus 1 is approaching 1. So this thing inside the ln is getting closer and closer to 1. So ln of that is getting closer and closer to ln of 1, and remember that ln of 1 is 0. So the second factor is approaching 0. The x goes to infinity, the ln of 1 over x plus 1 goes to 0. So that limit up there in the exponent has form infinity times 0. And that's something we can use L'Hopital's rule to handle. We need to bring either the x down to the bottom as a 1 over x, or the ln of 1 over x plus 1 down to the bottom as its reciprocal. Looks like it would probably be easier to bring the x down as a 1 over x. So let's do that. We get e to the power of limit as x goes to infinity. On top, ln 1 over x plus 1. On the bottom, we get the reciprocal of that x, 1 over x. And let's analyze what's happening there. Well, the 1 over x is turning into 0. That plus 1 is 1. And ln of that would be 0. So we're getting 0 on the top. And on the bottom, x is going to infinity, so 1 over x is approaching 0 as well. So this limit up here in the exponent has form 0 over 0. And that we can use L'Hopital's rule for. Let's do L'Hopital's rule here. On top, we'd have to take the derivative of ln of 1 over x plus 1, and we got to use the chain rule there. Remember, that is the derivative of 1 over x plus 1 over 1 over x plus 1. And the derivative of 1 over x plus 1 is negative 1 over x squared. So up on the top, we get this expression. We divide by the derivative of 1 over x, which is negative 1 over x squared. It looks like kind of a mess, but then notice the negative 1 over x squares cancel, and it simplifies rather nicely. We get e to the power of limit as x goes to infinity of 1 over x plus 1. And as x goes to infinity, this 1 over x turns into 0. So that plus 1 is 1. And we simply get e to the power of 1. And that equals e. So this limit, by our new trick, combined with our way of handling infinity times 0, resulted in an answer of e. This limit equals e. Before we move on to the next example, I want to point out that maybe this answer of e is not so surprising. Remember, way back when we first talked about the derivative of e to the power of x, we had a formula for e. And remember what that was? The formula for e was e is the limit as n goes to infinity of 1 over n plus 1 to the power of n. This limit that we just computed is exactly the same. The only difference is you have an x instead of an n. So it's not surprising at all that this limit worked out to be e, because that's the way e was defined in the first place. Example 3. Limit as x goes to 0 from the right of x to the power of x. It's pretty clear what indeterminate form this is. It's 0 to the power of 0. That's our last of the 3 new indeterminate forms. Let's apply our trick to this limit. So the first step is to replace that x to the power of x with e to the power of ln of x to the power of x. And then that exponent of x comes down in front of the ln. And let's move our limit up into the exponent so we get e raised to the power of this number. So we need to work out this limit. X is going to 0, so the first factor x approaches 0. And what about the second factor ln of x? Remember that the limit as x goes to 0 from the right of ln of x is negative infinity. So this limit has form 0 times infinity. And we know how to handle limits of such a form. We could bring the x down to the bottom as a 1 over x, so we get e to the power of limit as x goes to 0 from the right of ln of x over 1 over x. Now as x goes to 0 from the right, the numerator ln of x goes to negative infinity, and the 1 over x goes to positive infinity. So this limit up in the exponent has form infinity over infinity, and that we can apply L'Hopital's rule to. We replace the ln of x with its derivative 1 over x. We replace the 1 over x with its derivative negative 1 over x squared. And before moving on, look for some simplification here. Reciprocate the bottom, multiply by the top. This simply becomes e to the power of limit as x goes to 0 from the right of negative x. That's an easy limit. That limit just equals 0. So we get e to the power of 0, and that's 1. So in our third example, we resolve the limit of the form 0 to the power of 0. So we've done 3 examples for each of our 3 new indeterminate forms. And that's it for today. You should get lots of practice with this. Let me just give you a summary of the last 3 lectures, including this one. We saw that there were 7 indeterminate forms listed here. And we had L'Hopital's rule, which dealt explicitly with the first 2 indeterminate forms. The other 5 indeterminate forms we came up with algebraic techniques for to reduce them to L'Hopital's rule problems. And here's a quick summary: how to evaluate limits of these 7 indeterminate forms. If you have form 0 over 0 or infinity over infinity, just apply L'Hopital's rule. If you have form 0 times infinity, write that limit as x approaches c of f of x times g of x as the limit as x approaches c of f of x over the inverse of g of x. It's reciprocal. Or bring the f of x down. And you'll get an indeterminate form 0 over 0 or infinity over infinity when you do that, and you apply L'Hopital's rule. For infinity minus infinity, we consolidate into a single fraction and apply L'Hopital's rule. For our last 3 indeterminate forms, the topic of today's lecture, we learned to write the limit as x approaches c of f of x to the power of g of x as the limit as x approaches c of e to the power of g of x times ln of f of x. And that converts to an indeterminate form 0 times infinity, and we handle that as above. It's important, of course, to work lots of exercises to learn how to do this. Just watching the lectures is not enough. So please do that. This concludes today's lecture, and it also concludes part 4 of the course on applications of derivatives. In this series of lectures, we learn to apply derivatives to the problems of evaluating limits. Next up, we'll begin part 5 of the course on integration. I'll see you then, and goodbye.